Welcome back to the workshop. Module 6 is an overview and discussion of the flexible and semi-rigid pavement design strategies. Module 6 overviews and discusses the flexible and semi-rigid pavement transfer functions and models and how they are used to design flexible and semi-rigid pavements using the Pavement ME design software. We just completed Module 6-1 on flexible pavements, and will now begin Module 6-2 on semi-rigid pavements. So Module 6-2 focuses on semi-rigid pavements design strategies. We just finished explaining the distress prediction models and transfer functions used for flexible pavement. This session or module of Module 6-2 will focus on the distress prediction models and transfer functions for semi-rigid pavements. These include rutting, transverse cracking, top-down and bottom-up fatigue cracking of chemically stabilized base layers, reflection cracking, and then smoothness degradation of semi-rigid pavements. There are 7 learning outcomes for Module 6-2 on semi-rigid pavement design strategies and the distresses associated with semi-rigid pavements. The first is to define semi-rigid pavement as it applies to the use in the MEPDG. The second is to identify the semi-rigid pavement distresses that are common and the same as for flexible pavements. The third is to describe the semi-rigid pavement models and transfer functions for fatigue cracking of chemically stabilized base layers. The fourth is to describe the semi-rigid pavement transfer functions for transverse and fatigue reflection cracking. The fifth is to describe the semi-rigid pavement regression equation for smoothness degradation, or IRI. And the sixth is to identify the input variables to change to achieve an acceptable semi-rigid pavement design. Before getting into the details of the flexible pavement transfer functions that are used in design, Chapter 3, or specifically Section 3.3 on new flexible pavement and asphalt overlay design strategies, which also include semi-rigid pavement designs, include information on these strategies. Semi-rigid pavements are listed and briefly discussed under the flexible pavement and asphalt overlay sections. So now let's open the MEPDG manual of practice and briefly go through these different sections in terms of what will be covered within this module on semi-rigid pavement design. So we're going to go to section 3.3 in chapter 3 and very briefly go over the semi-rigid pavement. So 3.3 is on new flexible pavement design and asphalt overlay design strategies that are applicable to the MEPDG. We've already discussed and went over in the last, or Module 6.1, conventional flexible pavements, deep strength flexible pavements, and full depth asphalt pavements. Semi-rigid pavements is what we're discussing as part of 6-2, and there's a short discussion on what the meaning of semi-rigid pavements is within the MEPDG. Also, Figure 3.1 does include a cross-section of optional layers that are used or can be used for semi-rigid pavement design strategies. So we're going to go back now to the presentation and basically continue. That's only was a short kind of brief information in chapter 3 itself. So the contents for this module are grouped into 5 parts. The first one is definition of semi-rigid pavements. Then we'll get into design features and factors of semi-rigid pavements. We'll discuss the models and transfer functions that are used for semi-rigid pavements. We'll also briefly review adjustments that can be made for semi-rigid pavement designs to achieve an acceptable pavement design. And then finally, we'll go through the summary of what we covered within this module. So we're going to start with the definition of semi-rigid pavement as it applies to the MEPDG. Basically, a semi-rigid pavement consists of an asphalt layer, one or multiple layers, that are placed directly on a chemically stabilized base or subgrade, but more importantly, that chemically stabilized base or subgrade has flexural strength that can resist tensile stresses. Under Module 4-4-3, we explained and described the layer properties that are required for a chemically stabilized layer in accordance with using the Pavement ME design software. A specific note to make: a granular or unbound layer cannot be placed between the chemically stabilized layer and asphalt layers because that would violate the specific definition for semi-rigid pavements. So if a user does have a situation, for example, where the subgrade has been stabilized with soil cement, and that stabilized soil cement has flexural strength and can resist tensile stresses for the soil cement, and then a granular material is going to be placed between the soil cement and asphalt layers, that would, in terms of the MEPDG, be defined as a flexible pavement, and the soil cement would be simulated as a high modulus or high representative modulus of the soil cement, and it is assumed that the granular material that's being placed between the soil cement and asphalt layer would prevent any transverse cracks or shrinkage cracks in the soil cement, as well as fatigue cracks, from reflecting up through the asphalt layer. So it would be simulated as a flexible pavement rather than a semi-rigid pavement. This module, Module 6-2, is going to focus on the specific definition of semi-rigid pavements where the asphalt layers are placed directly above a chemically stabilized layer. So different materials or additives can be used in the chemically stabilized layer. These can include Portland cement, lime fly ash, and different combinations, as well as other cementitious types of materials. So this is where we have a cement stabilized base, cement fly ash stabilized base, soil cement that's placed, and then the asphalt layers are placed directly on that chemically stabilized layer. And that would qualify as a semi-rigid pavement in terms of the MEPDG. However, simply adding Portland cement, lime, or lime fly ash combinations does not mean that that pavement would qualify as a semi-rigid pavement. In other words, simply adding cementitious material would not qualify as a chemically stabilized layer within the Pavement ME design software. It depends on the type and amount of additive mixed in with the aggregate or other materials. In other words, the material that's added. A sufficient amount of material needs to be added to the aggregate so that a mixture with flexural strength and can resist tensile strains is the end product. This slide simply illustrates in the form of a graph as the percent additive increases, whatever that additive is, the strength and or stiffness of the mixed material will also increase, going from a lime stabilized soil to like more of a lean concrete. Adding lower percentages of lime to a soil does not change how the soil will respond to loads. However, adding a higher percentage of Portland cement will change the response of the aggregate or soil to a bound layer. The question is, when does the chemically stabilized layer start responding as a bound layer that is susceptible to fatigue cracks for other chemically stabilized layer? As an example, adding a minimum amount of lime to a soil, say a high plasticity soil, will not mean that that layer will be a bound layer and can resist tensile stresses or will have flexural strength. However, if we start adding material like Portland cement above, say, about 5%, then the combined material starts to behave as a bound layer, which does have flexural strength and can resist tensile stresses. So there's a combination of materials, and obviously there is a gray area where it's dependent upon the amount, the type of aggregate, and other factors on whether that material will respond as a bound material or as an unbound material. These go from a lime stabilized soil, cement, fly ash stabilized soil, to a cement, fly ash, or lime modified soil, cement treated base, cement aggregate mixture, roller compacted concrete, and finally lean concrete. So if in general an intact core cannot be recovered from the compacted material, then it is generally assumed that it is behaving or will behave as an unbound layer. And that's generally where the amount of additive is less than about 4%. However, if we've added enough additive, say above 5%, and an intact core can be recovered, as shown in the photo, we get an intact core of that chemically stabilized layer, then it is assumed that layer is responding as a bound layer, has flexural strength, and can resist tensile stresses. So that is the definition of a chemically stabilized layer. And section 6-2 will focus on this area here, where we have higher amounts of percent additives that are added. Lower percent additives that may be mixed in with the material, these are assumed to respond as an unbound layer and would apply to the flexible pavement design strategy and would be simulated as an unbound layer. So we will move forward within this module basically under this definition where the chemically stabilized layer have flexural strength. In other words, enough additive has been added. So the layer is responding as a bound material with flexural strength. This table simply shows a brief summary and or overview regarding the description of chemically stabilized layer cement treated base type materials. Both kind of an average compressive strength, average elastic modulus, and average flexural strength. And it simply shows that if we have enough additive or a high strength type material, no question intact testable cores can be recovered. The compressive strength on the average, kind of as a default value, would be about 1400 psi. The average kind of default value for an elastic modulus, it should be above 2 million psi, and an average flexural strength for a default value would be in the range of about 350 to maybe 400 psi. A moderate strength, where cores still can be recovered, but they may not be testable. In other words, they're not smooth cores. Some of the material may be degraded from the core. So these kind of would be referred to as moderate strength. Cores can be recovered, but they may not be testable in the laboratory. Compressive strengths of these on the average default value may be 500 psi. An elastic modulus default average value may be around 1 million or slightly less psi. And then the flexural strength average value or default would be somewhere around about 200 psi. If we've added a lower amount of additive where the cores cannot be recovered, that's considered a low strength type material. And in this case, the semi-rigid pavement simulation is not applicable regarding the MEPDG. So it is, or the user should assume, a conventional flexible pavement, and that low strength layer with the additive would be simulated with a high stiffness aggregate type layer. So now let's move to the design features and factors since we have defined what a chemically stabilized layer is within a semi-rigid pavement design strategy of the MEPDG. So this is a screenshot showing the folder and tabs for the semi-rigid pavements. Semi-rigid pavement design features and factors that are needed for designing a semi-rigid pavement in accordance with the Pavement ME design software. So the software will now open the software to show where the semi-rigid pavement design features and variables and properties are basically located. So we're going to go to the software. We'll look at the general information for basically semi-rigid pavements, and then we're going to go through those tabs or folders that are applicable. We're going to start first of all with the design performance criteria and kind of just briefly mention the values that are used. So we have the initial IRI, just like with any other pavement design strategy. We have AC thermal cracking, AC bottom-up fatigue cracking, AC top-down cracking. This amount of cracking is for the new asphalt layer. Then permanent deformation in the asphalt, total permanent deformation or rutting, right? Total pavement rutting and rutting in the asphalt layer. And this is only for the asphalt layers themselves. We then have the terminal IRI representing failure from a functional standpoint. That's the same for all the pavement design strategies. And then for our semi-rigid pavements, we have 3 new design criteria based on what we discussed for flexible pavement. The first is the chemically stabilized layer, the fatigue fracture or fatigue cracking of the chemically stabilized layer. And then we have AC total fatigue cracking, which includes bottom-up cracking from the asphalt layer, and then the reflection of the fatigue cracks from the chemically stabilized layer through the asphalt surface layers in terms of total bottom-up plus reflective cracking from the chemically stabilized layer. Similarly, we also have the total transverse cracking in the asphalt layer, plus the reflection of shrinkage cracks in the chemically stabilized base layer that are combined with new transverse cracking in the asphalt layer. So it's the combination of new transverse or thermal cracks plus reflection of shrinkage cracks in the chemically stabilized layer. And so the reliability is the same as for for flexible pavement design. However, a quick note here is that there is a reliability of 50% that the user cannot change for selected performance criteria. That would be new AC thermal cracking or transverse cracking, new AC bottom-up fatigue cracking, and then the fatigue cracking in the chemically stabilized layer. The reason these are 50% for which the user cannot change is that they are included in the total fatigue cracking, bottom up plus reflective, and total AC transverse cracking, thermal plus reflection of shrinkage cracks that are included in the fatigue of the chemically stabilized layer, as well as in the cracking, thermal cracking and bottom-up fatigue cracking in the asphalt wearing surface. So the reliability is only applied to the total rather than the individual distresses of the semi-rigid pavements. So now with the performance criteria, traffic is the same as flexible. Climate is the same as what we've previously discussed for rigid and flexible. Structure in terms of the material properties is the same for all of the layers with the exception of the chemically stabilized soil layer. So with the chemically stabilized soil layer, we have the low transfer efficiency of that chemically stabilized layer, and we'll define these in more detail when we get back to the presentation. We also have the low transfer efficiency regarding the transverse cracks of the chemically stabilized layer or the shrinkage cracks. And then we have the crack spacing or the shrinkage crack spacing of the chemically stabilized layer that are inputs to the software. So we have two low transfer efficiency values, one for fatigue, one for transverse cracking, and then the crack spacing for the shrinkage cracks in the chemically stabilized layer. The cement base, typically Poisson's ratio and unit weight, those were discussed in Module 4-4-3. We're not going to review those now. The cement base strength was also discussed in Module 4-4-3 on the inputs. But for that chemically stabilized layer, we do have the 28-day modulus of rupture. We also have the 28-day elastic or resilient modulus. And then we have another term called the minimum elastic resilient strain. We will define these in the further in the presentation on semi-rigid pavements. But these are the cement-based strength values that are applicable to all chemically stabilized layers. Modulus of rupture, elastic resilient modulus, and then this minimum elastic resilient modulus. The cement-based thermal properties is basically the heat capacity and thermal conductivities. These were also discussed in Module 4-4-3 on material inputs, and so we're not going to reiterate those. The next would be the maintenance strategy for chemically stabilized material. It's identical to flexible pavements because there is an asphalt wearing surface. So the same type of non-structural maintenance activities apply to semi-rigid pavements as was discussed for flexible pavements. So that's really no difference. We're now going to go down to the design properties for semi-rigid. Those are identical to what we discussed for flexible pavements in Module 6-1. And they include the asphalt surface shortwave absorptivity, layer interface, endurance limit, and the multi-layer rutting calibration coefficients. Those are identical to what was discussed for flexible pavements. So we're not going to discuss those in detail because they've already been discussed under flexible pavements. What we will review is the calibration coefficients. The calibration coefficients for the asphalt bottom-up, top-down cracking, as well as asphalt fatigue, asphalt rutting, are basically all the same as for flexible pavements because it's the same asphalt material, whether it's placed on a semi-rigid pavement or a flexible pavement. We're also the subgrade rutting, base rutting are the same. The thermal fracture of the asphalt wearing surface is the same. What's different is the chemically stabilized mixture fatigue, and this is the chemically stabilized fatigue coefficients K1, K2 that are measured in the laboratory. We will go over these in the presentation and define these later in this module. And then we have the laboratory calibration coefficients, the BC1, BC2, that are consistent with K1 and K2 from a laboratory fatigue standpoint. And again, we will define these when we talk about the mechanism and the transfer functions. The other thing, we have the chemically stabilized mixture in terms of cracking. This is the calibration coefficients for the transfer functions, C1, C2, C3, and C4. We'll also discuss and define these later in the presentation specifically, but this is where they're located within the software. And then the standard deviation of the chemically stabilized material, which you can see is 1, unity. And the reason for that is the reliability, as we just previously mentioned, is not applied to the fatigue cracking of the chemically stabilized layer. The reliability or standard deviations of the residuals is applied to the total fatigue cracking that includes the cracking in the fatigue cracking in the chemically stabilized base added to any new fatigue cracks in the existing or in the upper asphalt layers. So it's not applied, reliability or the standard deviation of the residuals is not applied just to the chemically stabilized layer. The last item or tab we'll review is the IRI. And the IRI we've discussed already under flexible pavements, IRI flexible, the calibration coefficients of the regression equation for C1, C2, C3, C4. IRI flexible over PCC, the calibration coefficients for C1, C2, C3, and C4 relate to both semi-rigid asphalt over chemically stabilized layer, as well as asphalt overlays placed over rigid pavements. So these are the calibration coefficients for the IRI regression equation. The IRI standard deviation of residual modules is the same for both semi-rigid as well as flexible pavements. And so there's only one standard deviation of the residuals that are included in the Pavement ME design software itself. So with that, we'll now return to the presentation and simply continue with the discussion of the models and transfer functions, as well as calibration coefficients. So coming back to the presentation, we're going to go through each of the design features, the properties, and other information as it relates to the models and transfer functions for semi-rigid pavements. These will be covered towards the latter section within this module. Specifically, we're going to focus on some of the structure, calibration, and design properties themselves. So these, the five features or factors as it relates to semi-rigid pavements: asphalt, short-wave absorptivity, layer interface, the endurance limit, multiple layer, rutting calibration, and the maintenance strategy. These five items were previously discussed for flexible pavements, and they're identical in definition, meaning, as well as the default values also for semi-rigid pavements. So we're not going to discuss them in detail specifically for this module of semi-rigid pavements. They're identical to what was discussed for flexible pavements. So the next item is the models and transfer functions used for semi-rigid pavements. So before getting into the details of the transfer functions and our models that are used in semi-rigid pavement design, Chapter 5 in the MEPDG Manual of Practice includes and discusses the distresses, the models, the transfer functions that are used in the design of semi-rigid pavements. Specifically, Section 5.3 is on the distress prediction equations for flexible and semi-rigid pavements. So now let's open the MEPDG Manual of Practice, and we'll briefly go through these different sections or the specific sections in terms of what we're going to be covered within this part of Module 6-2 on semi-rigid pavement design. So we're going to come back to the Manual of Practice, and we're going to go to the section where it discusses performance indicator prediction methodologies and specifically load-related cracking and reflection cracking. So we're going to go through both of these sections. So 5.3 load-related cracking, we've already covered bottom-up fatigue cracking that's included, as well as the top-down cracking. But for the chemically, cement-treated base layers or chemically stabilized mixtures, this shows and briefly discusses the fatigue strength and transfer function for predicting the fatigue cracking in that chemically stabilized layer. That's discussed within this section 5.3.3, but specifically for chemically stabilized mixtures. And when we go through these, you'll see these equations: the fatigue strength equation, the transfer function, and then this minimum elastic modulus equation that we'll discuss in greater detail in the presentation. The other item I want to go over or mention with it's in the manual of practice has to do with reflection cracking of asphalt overlays, including AC layers of semi-rigid pavements. And we're going to discuss this because it's a design criteria or distress variable for semi-rigid pavements. So this is the reflection cracking of fatigue and transverse cracks. It basically covers the different mechanisms and then goes over the fracture mechanics approach in accordance with the Paris law on how reflection cracks are predicted within the Pavement ME design software. So we'll come back to this section, or not back to the section, but we'll cover many of these mathematical models, equations within the presentation itself, as well as the transfer function for predicting the reflection of the rate of reflection cracks. Basically, the total area of cracking. And this simply lists the calibration coefficients, these tables for reflection cracking. So we're going to go back to the presentation now, and we'll continue and cover the models and transfer functions as part of the presentation. So this is a screenshot that we started with for semi-rigid pavements in the Pavement ME design software. The distresses or performance criteria for semi-rigid pavements is displayed on this screenshot, which we previously reviewed in an earlier session of this module. The following slide will list each performance criteria, the models and transfer functions that are used to predict the distress values. In other words, those that are specific to semi-rigid pavements. Now, a mention of a couple of those that are where the reliability is set at 50%. We mentioned this when we had the software opened and discussed them. But for some of the performance criteria, the reliability is set at 50%, and the user cannot change that value. The reason for that is that the reflection cracks, the reliability is based on the reflection cracks or reflection cracking plus any new cracking in the asphalt layer of a semi-rigid pavement. So it's not applied to the individual thermal cracks that are new. The reliability is not applied to bottom-up fatigue cracking only in the asphalt layer, and it's not applied to only fatigue cracks in the chemically stabilized layer. The reliability is applied to the total fatigue cracking, bottom-up and reflective, that we can see and measure at the surface, as well as the total transverse cracking of thermal plus reflective shrinkage cracks from the chemically stabilized layer that we can see and measure on the pavement surface. So the distress or performance criteria for semi-rigid pavements is displayed on this screenshot, which we previously reviewed in an earlier session of this module. The following slide will list each of the performance criteria in terms of the models and transfer functions that are used for predicting the distress. But as displayed in the table, many of these transfer functions have already been discussed and described for flexible pavements because they are the same. So new asphalt transverse cracking, new bottom-up fatigue cracking, new top-down fatigue cracks, asphalt rutting, and total asphalt rutting was discussed in Module 6-1 on flexible pavements. These are identical to what is used for semi-rigid pavements. So we're not going to include those or discuss those within this Module 6-2. We will discuss the fatigue failure or fatigue cracks of chemically stabilized layers. We will discuss the total transverse crack, new and reflective. We will discuss total bottom-up fatigue cracks, new and reflective, as well as the terminal IRI that is specific, all of these being specific to semi-rigid pavements. So the remainder of the models and transfer functions that are specific to semi-rigid pavements are discussed within this session. So only 3, fatigue cracking, total fatigue cracking, or fatigue cracking of the chemically stabilized layer, reflection cracking, fatigue and transverse, and smoothness degradation. These are the only 3 distress variables that will be discussed within this model on semi-rigid pavements. We will start with the fatigue cracking of the chemically stabilized layer, the model and transfer function on how the Pavement ME predicts fatigue cracking of the chemically stabilized layer. So bottom-up fatigue cracks, even for the chemically stabilized layer, are caused by repeated application of traffic loads. The repeated tensile stress at the bottom of the asphalt layer are applied at a given point that develops micro cracks, which eventually form a fracture and then propagate through the chemically stabilized layer. This is very similar to the paperclip experiment that we've already discussed in terms of the paperclip experiment from Module 2 that we've already reviewed and discussed for rigid pavement fatigue cracking as well as asphalt fatigue cracking. So the bottom-up fatigue cracking for chemically stabilized layers is no different. The fatigue strength of the material basically defines the allowable number of load applications. The critical response calculation for semi-rigid is tensile stress, which we'll define in a second. And then the allowable number of load applications, which is basically the fatigue strength of the stabilized mixtures, are used to determine damage. So the fatigue cracking mechanism is defined by these 3 parameters or variable, similar to the paperclip experiment and almost identical to what was used for Portland cement concrete fatigue as well as asphalt mixture fatigue. So there are the critical response calculation, the material strength of the chemically stabilized layer, and then the allowable number of load applications for a chemically stabilized layer. So we're first going to start with the critical response location. Critical response calculation. As previously noted earlier in this model, the Julia is an elastic layered program that the Pavement ME software uses to compute critical responses, both for flexible as well as semi-rigid pavements. So the Julia program is used to calculate critical pavement responses for predicting the distresses, specifically fatigue cracking of the chemically stabilized layer itself. and that is the horizontal tensile stress at the bottom of the chemically stabilized layer. Again, only if that layer has flexural strength and can resist tensile stresses. So, horizontal elastic tensile stress at the bottom of the chemically stabilized layer, is the critical layer response, which is used to predict the fatigue cracking of the chemically stabilized layer. The horizontal tensile stress is basically defined by the Poisson's ratio of that layer, the layer stiffness of the chemically stabilized layer, and then the layer thickness as well as the stiffness of the asphalt layers above the stabilized layer, and then those layers supporting the chemically stabilized layer. So now moving to the material strength of a chemically stabilized mixture. So we'll now identify the material strength as used in the distress mechanism for predicting fatigue cracking in semi-rigid pavements. Very simply, AASHTO T97 is used to estimate or measure the flexural strength or the modulus of rupture of the chemically stabilized material. And ASTM DC469 is used to measure the elastic modulus of that stabilized material. So remember the different input variables for the chemically stabilized layer as a review from Module 4-4-3. The 28-day compressive strength, or the modulus of rupture, is measured in accordance with AASHTO T97. And then the 28-day elastic modulus is measured in accordance with ASTM C469. The MEPDG, or the Pavement ME design software, also provides some regression equations or rules of thumb for estimating the flexural strength as well as the elastic modulus from the compressive strength. So the rule of thumb is that 20% of the unconfined compressive strength, 20% of the unconfined compressive strength can be used to estimate the flexural strength itself. So that's a rule of thumb that's noted in a regression equation in the MEPDG Manual of Practice. The elastic modulus can also be calculated from the compressive strength. So we have values that can be measured in the laboratory for flexural strength and elastic modulus. But as the material becomes slightly weaker, but still has flexural strength, measuring those values in the laboratory, flexural strength and elastic modulus becomes more difficult. So doing a simple compressive strength is typically used, and then that compressive strength is used to estimate the flexural strength and the elastic modulus of that stabilized layer, which can be used as inputs to the Pavement ME design software. And this just shows some, which we've previously covered. This shows some examples, kind of some default values for what were considered the high strength, moderate strength, and or low strength chemically stabilized material. Again, to mention this again, if the material cannot be cored, the chemically stabilized layer cannot be cored, then that would not be considered appropriate or applicable to a semi-rigid pavement. And the user would simply assume a conventional flexible pavement design strategy where that stabilized or treated layer would have a higher stiffness for the stabilized layer that could be moisture dependent. It also could be constant throughout the design life of the pavement. And then the high strength and moderate, where we can recover cores of the material. And these are typically, that we've already mentioned, the default values or some average values that can be used for default. So in summary, the MEPDG fatigue model for chemically stabilized material is used to determine the allowable number of load applications. And this regression equation was defined from field loadings and, more importantly, laboratory testing of chemically stabilized mixtures, which is shown on this slide. So the allowable number of stress applications to failure or cracking is defined by this regression equation. Note that the tensile stress, sigma T, tensile stress at the bottom of the chemically stabilized layer divided by the modulus of rupture or flexural strength of that layer is the similar ratio that was presented in Module 5 on fatigue cracking for defining allowable number of load repetitions for the Portland cement concrete layer. The coefficients, calibration coefficients, the beta values, as well as the laboratory values or values determined from laboratory tests are shown here and obviously are different from Portland cement concrete. So again, the M sub R, the modulus of rupture or flexural strength, can be determined from AASHTO T97 or estimated from the compressive strength. And tensile stress is simply calculated by Julia at the bottom of the chemically stabilized layer. And the calibration coefficients are basically used to define the allowable number of load repetitions. And similar for fatigue cracking, this ratio, tensile stress over modulus of rupture or strength, was used or is used to normalize the fatigue strength of different chemically stabilized layers or mixtures, similar to the reason for different Portland cement concrete mixtures under fatigue cracking of Portland cement concrete. So now let's move to the fatigue damage accumulation. The fatigue cracking mechanism includes calculating the incremental fatigue damage of chemically stabilized layers and then summing those incremental damage indices to determine the total fatigue damage over time within the chemically stabilized layer. This section of the module will explain and discuss the accumulation of fatigue damage, which in concept is the same as for Portland cement concrete as well as asphalt. So first, the definition of incremental fatigue damage accumulation is shown on this slide in terms of how it's determined. Again, very simply, fatigue damage is simply the actual number of load applications, little n, divided by the allowable number of load applications, big N. The same was true for Portland cement concrete as well as asphalt. The fatigue damage accumulation is basically determined by accumulating the incremental fatigue damage, in other words, actual number of load applications, divided by the allowable number of load applications on a traffic basis, different types of trucks, different types of axle loads, as well as in different seasons and years within the design life of the pavement. The allowable number of load applications from the previous slide is simply shown here on how it's determined for calculating damage within a specific time increment and or traffic load increment. And that's related to the ratio of tensile stress divided by the flexural strength or strength of the chemically stabilized material. Now, the Pavement ME design software gives the user the option to reduce the chemically stabilized mixture to a minimum value that would basically represent the total damage or destruction of the chemically stabilized layer from the accumulation of damage, as shown in this regression equation. So the reduced E value, or the minimum E value, shown in the regression equation, we mentioned when we had the software open. So the inputs to the model or to the software are the 28-day strength or the modulus of rupture, the 28-day elastic modulus, which would be Emax of the CTB. That would be the 28-day value, and then a minimum value of the CTB. And again, this minimum value would represent the extreme fatigue cracking of the chemically stabilized layer. So as this layer becomes fully cracked, the modulus of the layer will decrease, or is expected to decrease, to a minimum value similar to a very high aggregate base type of material, representing the totally cracked chemically stabilized layer. However, let's go back to the software, and this shows the inputs to this minimum elastic modulus value that's included in the regression equation. And then once we know the minimum value, once we know the 28-day turn maximum modulus value that's entered into the software, we can then estimate with additional damage how the modulus of that chemically stabilized layer at any point in time, what that modulus will be, depending on the damage from the damage index calculated by the software. In other words, the accumulation of damage defined by the actual number of load applications divided by the allowable number of load applications. So that was the definition or use of letting the modulus of the chemically stabilized layer decrease as damage gets to accumulate. However, that modulus reduction is not applied to the asphalt layer in terms of design. It's also not applied to the Portland cement concrete layers for rigid pavement design. So in concept, we're going to go through what this means if used, if a minimum elastic modulus value is used. What does that mean in terms of a fatigue, damage, and design for a semi-rigid pavement? So what this graph shows is the concept of the elastic modulus reduction with increases in fatigue damage, which is illustrated in this slide. As the chemically stabilized layer is subjected to increasing traffic loads and increases in fatigue damage over time, because the number of actual traffic loads is increasing over time. The elastic modulus of the chemically stabilized layer decreases to an effective modulus value represented that is represented of total fatigue failure of the chemically stabilized layer. So the graph shows age or time in age on the horizontal axis versus the modulus, calculated modulus, based on fatigue damage, the damage index of the chemically stabilized layer, how that modulus decreases with time or with increasing actual number of load applications. And these values then would be used in the calculation of tensile stress with additional fatigue damage and additional traffic loads applied to the semi-rigid pavement. So to further explain this concept that is shown in this graph or illustration. So the solid black line represents or mean that there is no modulus of reduction. In other words, going back to the previous slide, E minimum is equal to E max. So there is no reduction in the modulus with increasing fatigue damage throughout the design life of the semi-rigid pavement. So if we do not have any reduction, this solid line shows no reduction as an example of bottom-up or fatigue damage in the chemically stabilized layer as a function of age and or time. And this is for a modulus of rupture or flexural strength of 450 psi with an E minimum of 1,500,000 psi. Again, this would be equal to the 28-day elastic modulus. No reduction in modulus. The short dashed line is representative of a chemically stabilized layer that has 450 psi flexural strength, and the E minimum is 150,000. So there is a modulus of reduction. And you can see the significant reduction of the fatigue damage in that layer over time by simply using an E minimum and allowing the modulus to decrease over time with additional fatigue cracking of the layer. The last example is a longer dash line, and this represents a flexural strength of the stabilized layer of 600 psi with an elastic modulus minimum of 150,000 psi, similar to the other example. And again, it's significantly the calculated elastic modulus becomes very low because the fatigue damage is increasing over time. So the increase in fatigue damage basically increases, but at a substantial decreasing rate. So it's more of for the no reduction in the elastic modulus, the fatigue damage accumulates at a faster rate than for the condition when we have a reduction in modulus to account for the cracking of that stabilized layer. So continuing, what does that mean in terms of design? And that's illustrated in this figure here, or this graph. So one of the things to remember, the pavement ME design, or the MEPDG process, does give the user an option to enter a minimum elastic modulus to account for cracking of that stabilized base layer. However, the flexural strength does not decrease. It remains constant. So the amount of fatigue damage will decrease, or incremental fatigue damage will decrease as the modulus decreases. The reason for that is related to this graph. This graph shows the elastic modulus of the stabilized material versus the tensile stress at the bottom of that layer. So as the modulus decreases, so if we start out at about 2 million psi elastic modulus, and we allow that to go down to very low values of 150,000 psi, the tensile stress at the bottom of that layer becomes very small. What doesn't change is the strength of the material, or the flexural strength, the MR. So as the tensile stress decreases, while the modulus of rupture or flexural strength remains constant, this ratio becomes very small, and thus the allowable number of load applications becomes very large. So the increasing fatigue damage, the incremental fatigue damage, becomes very small. So that is the reason why the accumulated fatigue damage, when we consider a reduced modulus, the increasing or incremental increase in fatigue cracks increases, but at a much decreased rate compared to no modulus reduction. So is this reasonable? So the suggestion is that it is not, that we have very long lives, or we can determine very long lives of semi-rigid pavements by using the reduction of the elastic layer modulus concept. So the suggestion is to assign the minimum elastic modulus equal to the 28-day elastic modulus that's measured in the laboratory, or that's used as a default value for the 28-day elastic modulus. And again, none of the other bound layers, asphalt or Portland cement, includes this modulus reduction in the fatigue analysis of those materials. So the MEPDG manual of practice suggests that that same concept or same assumption be applied to chemically stabilized layer. In other words, do not consider the reduction in elastic modulus as damage increases. Simply set the minimum elastic modulus of the chemically stabilized layer to the 28-day elastic measured modulus in the laboratory, or the 28-day default value. So setting, kind of remember, the 28-day elastic modulus decreases with damage if we're using the modulus reduction, but the 28-day strength value does not decrease with damage. The result can be extremely high allowable number of load applications or very long lives of relatively thin semi-rigid pavements. So again, the suggestion is to simply set the minimum value, E minimum in the software, equal to the 28-day elastic modulus that's measured in the lab. So that's the suggestion in the MEPDG manual of practice. And that is shown here as the minimum elastic modulus should be equal to the 28-day elastic or resilient modulus measured. If it's measured in the laboratory at 1.5 million, then the minimum elastic modulus should be 1.5 million, because the modulus of rupture is not going to change throughout the design life, the value that's entered by the user. Okay, for any chemically stabilized material that exhibits flexural strength, the relationship between flexural strength and elastic modulus becomes important to determine the fatigue characteristics of that chemically stabilized layer. We reviewed this concept as part of Module 5 when we were discussing the fatigue characteristics of Portland cement concrete, those measured in the laboratory and as applied in the Pavement ME design software. So for chemically stabilized layers that have sufficient flexural strength, that same concepts or fatigue concept applies to the stabilized base layers. This graph exhibits a relationship between the 28-day elastic modulus and 28-day flexural strength for which the magnitude of fatigue cracking at the end of the design life is the same for different combinations of elastic modulus and flexural strength. The relationships are dependent upon the thickness of the asphalt layer above the stabilized layer. So in the Pavement ME software, there is unique relationships that can be developed between elastic modulus and the 28-day flexural strength, at which, at the end of the design life, everything else being equal, the predicted fatigue cracking of the semi-rigid pavements would be the same. So there would be no difference within these lines that are a function of asphalt layer thickness. They would give us the same amount of cracking with these different combinations of elastic modulus and flexural strength. The closed blue circles are an asphalt layer thickness of 2.1 inches. The solid black line is an asphalt layer of 5.6 inches. And then the closely spaced dashed line is for 5.6 inches. 3.9 inches. So again, the longer dashed line is 2.1 inches. The solid line is 5.6 inches of asphalt. And then the short dashed line is 3.9 inches of asphalt. So they're very close to being the same, all other factors remaining constant. So any combination of elastic modulus and flexural strength that are above this line would be more resistant to fatigue cracking. Because, for example, a million at a strength of 250. If at a million elastic modulus and a strength of 300 psi, that means the damage or the ratio is going to be less because the modulus of rupture is now greater. And so we'll have a greater allowable number of load applications and lower damage. So it's more resistance to fatigue damage. Conversely, if our combinations of elastic modulus versus strength plot lower than these relationship, that means those materials or layers are going to be less resistant to fatigue cracking, or we're going to calculate, or the program's going to calculate more fatigue cracking. So below the line, we'll calculate more fatigue cracking. Above the line, we're going to calculate less fatigue cracking within the chemically stabilized layer. Again, the concept is the same as was discussed for Portland cement concrete in Module 5. So this kind of unique relationship makes the analysis of semi-rigid pavements, if if we know what these relationships are for our materials, then this provides a good comparative analysis on the thicknesses that are going to be required based upon measured strengths and elastic modulus of the materials in the lab. So now let's move to the transfer function for chemically stabilized layers. So this is the transfer function for chemically stabilized layer. Obviously, it's a function of the damage index of the chemically stabilized layer, the accumulation of the damage index throughout the life of the pavement, and the calibration coefficient, C1, C2, C3, and C4. Damage index, remember, is defined by the allowable number of load applications, big N, which is, or allowable number of load applications, and the actual number of load applications divided by the allowable simply defines the damage index. The allowable number of load applications, as to remember, is the tensile stress at the bottom of the chemically stabilized layer divided by the flexural strength or strength of the chemically stabilized layer. So this slide basically shows the results of the global calibration for the laboratory values, derived values, the calibration, as well as the field calibration values of the transfer function. So the laboratory derived values, or the K values, for defining the allowable number of load applications, KC1, KC2, KC1 and KC2 are basically defined in the laboratory. The beta values are the calibration of the laboratory values. In this case, or in the case of the global calibration, they're basically 1.0. For the transfer function for predicting cracking in the chemically stabilized layer, the C values or derived from the global calibration using field data. And so the C1, the intercept basically is 0. C2 is 75. C3 was 2. C4 was also 2.0. One of the reasons why C2 is 75 and not 100 regarding 100% of the percent lane area that is cracked is that most of the cracks in the CTB, or the chemically stabilized layer, are going to remain within the wheel path area or very much adjacent to the wheel path area. So 100% was not derived during the global calibration for the C2 term. So now let's come back to the fatigue cracking reliability. We're going to, for the chemically stabilized layer, the fatigue fracture, what is the reliability? Again, remember it's set at 50%. You can't change that as a user. So the fatigue cracking reliability is not applied to the fatigue cracking of the chemically stabilized layer. It is fixed at 50%. The reliability is determined based on the total amount of fatigue cracking that we can see at the surface, including new and reflected from the chemically stabilized base layer, because that is what we can see and measure on the surface. So the reliability is not applied to the individual stabilized layer. It's applied to what we can see and measure on the pavement surface in total. So now let's move to reflection cracking. Two types of reflection cracks are predicted by the Pavement ME software. Reflection of fatigue cracks from the chemically stabilized layer, and the reflection of transverse cracks or shrinkage cracks from the chemically stabilized layers. Both are going to be discussed in this session and based on the fracture mechanics approach. So this section is going to review regarding reflection cracking, is going to review the different types of cracks related to a semi-rigid pavement, the fracture mechanics approach, the reflection cracking mechanisms, and then overviewing or explaining the transfer function. So we're starting with the types of reflection cracks. The software considers two types, fatigue and transverse cracks, and keeps them separated for all design strategies. So we're not just predicting reflection cracks in total, we're predicting reflection cracks from fatigue and reflection cracks from shrinkage or in a chemically stabilized layer. So based on the reflection cracking methodology is based on fracture mechanics. Key factors of that methodology include the impact of traffic from wheel loads, the temperature profile computed by the enhanced integrated climatic model embedded within the Pavement ME software, the asphalt mix and binder properties, and thermal stress computations done using the existing MEPDG design approach specifically for thermal fracture or transverse cracking, the utilization of the Pavement ME design asphalt material fracture parameter from Paris law, the A and the EN parameter that we've already introduced and discussed for the transverse cracking and flexible pavements under Module 6-1, and then the adapted or modified procedure for cracking to account for both longitudinal and transverse directions, specifically for alligator cracking. Because for alligator cracking, we can have both transverse as well as longitudinal in terms of the alligator cracking pattern. So both are applicable. The reflection cracking length is calculated using fracture mechanics and the Paris law. The tensile stress intensity factors were calculated from a finite element response program for many different structures, climate, and mixture conditions for both alligator and transverse cracks, just like it was done for the transverse cracking in flexible pavements due to thermal events. The results then from these computations of the stress intensity factors were used to develop artificial neural networks that are included in the Pavement ME design software to actually calculate and or determine the stress intensity factors both for transverse cracking as well as fatigue cracks. And as I said previously, this approach is very similar to the approach used for transverse cracks discussed in Module 6-1, as well as in the top-down fatigue cracks, also discussed in Module 6-1, but on for flexible pavements. The minimum and lower thicknesses, or the minimum or lower thickness for the chemically stabilized layer included in the analysis was about 6 inches for the layer in all of these computations to define the stress intensity factors. Thus, 6 inches represents the suggested minimum layer thickness for the chemically stabilized layer in semi-rigid pavement design. In addition, a granular base or subbase was assumed below the chemically stabilized layer, and all of the finite element runs to generate the artificial neural networks. However, in the current version of the software, version 3, which we're using as part of this workshop, it does not require a granular material to be placed below the chemically stabilized layer itself. The parameters of A and N are defined or shown on this slide, but they will be explained in our latter section of this module. So the fracture mechanics approach basically divides the computations of the stress intensity factor into two parts. One is related to the incremental application of wheel loads, which is more similar to top-down fatigue cracks using fracture mechanics for flexible pavements. And the other is used for incremental increases in crack growth related to thermal or temperature cycles, the difference in temperature cycles. And that is similar to the transverse cracking of flexible pavement that was also discussed in Module 6.1. So it basically applies both incremental increases in thermal cycles as well as in wheel loads in predicting the overall growth in the reflection cracks from a fatigue basis as well as from a thermal basis from the chemically stabilized layer. So the two parameters, the fracture parameters A and N, are defined here. The G1, G0, G1, G2, G3, and G4 are simply parameters of the power law, and MX is, or M's sub mix, as well as the sigma sub T, are from the mixture, the asphalt mixture itself. In other words, the relaxation of the mix, and then the tensile strength of the mix. So we'll define these more clearly in the following sections, or the following sections of this module. But basically, the G values are the coefficients of the power law. The M is a property from the relaxation of the mix, and sigma sub T is the tensile strength, and D sub I is simply a damage parameter related to the total thickness of the asphalt layer. The other unique application regarding the reflection cracking mechanism regarding fracture mechanics that's embedded in the Pavement ME software to predict reflection crack is that it groups the reflection cracking mode into three parts. Part 1 is shear, Part 2 is thermal, and Part 3 is bending. In other words, shear is where you have a fracture in the chemically stabilized base layer. As a wheel load goes across the surface of the asphalt, there's a differential deflection at the crack in the chemically stabilized layer, and also at the tip of the crack as the crack grows into the asphalt layers above the stabilized layer. So that differential vertical deflection from one side to the other side of the crack is what's referred to as the shear mode, or related to shear. The thermal mode is simply due to thermal cycling, where the chemically stabilized base layer is opening and closing depending upon the magnitude of the thermal cycles, and that is a tensile-related strain or deformation that also tends to drive at the crack tip, drive the crack toward the surface. The last one is the bending. And so when the load goes across the center of where this crack is, there's obviously a weakening at the crack in the stabilized layer. And so the amount of bending or deflection increases. And so the tensile strain above the crack from the bending due to wheel loads increases, and that also drives the crack upward to the surface. So it's the total reflection cracking is a combination of three modes: shear, thermal, and bending. And this table simply just summarizes what we just mentioned. So mode 1, differential vertical deflections across the cracks. Those are traffic induced. The crack initiates and propagates in shear. Mode 2 is the thermal expansion and contraction of joints and cracks. Those are thermal induced, and those cracks initiates in tension, but can also initiates in tension, but can propagate in tension and shear. The third mode is higher deflections across the crack, and which results in more bending across the crack. These are traffic induced, where the crack initiates in tension, but can propagate in tension and shear across the crack or through the asphalt surface. And that mathematically is simply shown on this slide here. So it's three modes: a bending mode defined here as delta KB. That's the increase in the stress intensity factors as a result in bending. The delta shear, which is an increase in the stress intensity factors from the shear mode. And delta T tension, which is the increase in the stress intensity factors from thermal cycles or direct tension. And so the change in crack length with the number of load cycles or increase in load cycles is related by adding the change in stress intensity factors from bending and shear get added together, while the change in crack length due to thermal cycles or tension simply get increased using the same fracture mechanics, but in the tensile mode or the tension mode. So it's a combination of these three modes of stress intensity factors. So which one is more important? This graph simply shows the total fatigue cracking, percent total lane area as a function of age, but it's broken down into the shear mode, the black line, the bending mode, kind of an orange line, and the thermal component or the thermal mode for the short dashed line. And you can see very clearly the shear mode contributes most of the reflection cracking potential for total fatigue cracks that can be measured at the surface of the asphalt. This is fatigue cracks that exist in the chemically stabilized layer and that are being reflected through the asphalt layer. So the shear mode is definitely more important in terms of fatigue. Similarly, this graph shows the total increase in total length of transverse cracks that we can see at the surface as a function of age. And this would be transverse cracks from shrinkage cracks in the chemically stabilized layer. And again, we can see that the shear mode, the increase in the shear intensity factors related to the shear component are much more important. The black line shows the shear component. Again, the orange line shows the bending component, and the short dashed line considers the thermal component. For both fatigue, reflection of fatigue cracks, reflection of shrinkage cracks in the chemically stabilized layer, the shear mode contributes most of the reflection cracking prediction of these cracks through the asphalt overlay itself. So now let's move to why that is the case, or not so much why that is the case, because it's predominantly related to the differential vertical deflection across the cracks, which is a very high contributor to the shear mode. But going into now the load transfer efficiency, which basically defines the differential vertical deflection and the shear component of the reflection cracking. So these are inputs to the Pavement ME design software that we previously went through at the beginning of this module. And there's three. The low transfer efficiency for the fatigue cracks that are in the chemically stabilized base, the low transfer efficiency of the transverse cracks or shrinkage cracks that are part of the chemically stabilized layer, and then the transverse crack spacing that basically represents the spacing of the transverse crack. So the low transfer efficiency of fatigue crack is a calibration parameter because it's difficult to really actually measure that in the field. The low transfer efficiency of transverse cracks can be measured and quantified in the field. So these values are the default values in the Pavement ME design software. The default values are also tied to the crack severity when we get to rehabilitation in modules 8 and 9. But these are for semi-rigid pavements when it's a new semi-rigid pavement. So these are default values that are included in the program, but certainly the designer can change it. It's suggested that the designer, without doing a recalibration, that 50% be used as the low transfer efficiency for fatigue cracks, because that value was derived from the global calibration process on the average. But the user can measure the low transfer efficiency, which we'll demonstrate in just a second with the following slides. Those can be measured in the field. So the user can change based on field measurements for the low transfer efficiency of the semi-rigid pavement. And again, this is the reflection of shrinkage cracks through the asphalt layer from the chemically stabilized base layer because it can be measured. The spacing of the shrinkage cracks are basically not determined by the software, but need to be entered by the user. And that spacing needs to be determined external to the software itself. And we'll come back to that point a little later in the presentation. So the transverse crack shrinkage spacing, generally about 10 to 50 feet. But again, that is dependent upon the type of material. And again, Pavement ME does not calculate that value. So the user has to determine it external to the software. So the impact, what is the impact of low transfer efficiency or crack severity on the reflection cracking? So the low transfer efficiency defines the differential vertical deflection across a crack measured at the surface or semi-rigid pavement. And that can be measured with the falling weight deflectometer, as well as other deflection testing means to know what is that differential deflection across the crack. The differential vertical deflection clearly defines the shear component of the stress intensity factor. The stress intensity factor defines the rate of reflection cracking propagation through the asphalt overlay. So it is absolutely the more critical one and or the more important one. The stress intensity factors regarding bending and the stress intensity factors regarding thermal cycles or temperature variations have an impact, but the impact is relatively small considering the impact of shear or the differential vertical deflections. This graphically illustrates that impact from a load transfer efficiency standpoint. So these two graphs illustrate the impact of load transfer efficiency. This is total fatigue cracking as a function of time on the upper graph. The green is a low crack severity or low transfer efficiency of about 85%. The blue is a medium or moderate severity crack, and that is about 50%. And then the red is a high severity crack, which has a low transfer efficiency of less than 40%, a low transfer efficiency of 40. And so you can see that for fatigue cracking, the reflection of fatigue cracking, that low transfer efficiency is extremely important on the time it takes for those fatigue cracks to reflect through the asphalt surfaces. For thermal cracking, basically the same thing is true. This shows the total transverse cracks, feet per mile, as a function of age. The green is the low crack severity, or about low transfer efficiency of about 85%. The blue is a moderate crack severity, which is about a low transfer efficiency of 50% or a little greater. And then the red is a low transfer efficiency of 40% or less for a high crack severity. So you can see that the transverse crack length predicted by the software is heavily dependent on the low transfer efficiency. So this is the chemically stabilized crack spacing that's entered into the software by the user. And this is the spacing of the shrinkage cracks, because when the semi-rigid pavement is initially built, it is assumed there are no fatigue cracks of the chemically stabilized layer. So the chemically stabilized layer shrinkage crack spacing, the shrinkage crack spacing is fixed throughout the design period. In other words, at whatever value the user enters, that remains constant, and there's no additional shrinkage of the layer throughout the design period. And that value has to be estimated external to the software, and the limits of the spacing are somewhere between between 10 to 50 feet. There are cases where the chemically stabilized layer is rolled with a very heavy roller to sort of pre-crack the chemically stabilized layer shortly after construction, obviously before the asphalt layer is placed, to crack the mixture at a much shorter crack spacing. If that is done, if the specification of the agency requires that the chemically stabilized layer be rolled and pre-cracked, then if the crack spacing is known and it varies between 10 to 50 feet, that can be used in the software. If it's a more severe types of cracks that are much less than 10 feet, then the chemically stabilized layer can be simulated in the flexible pavement design strategy, but the chemically stabilized layer is no longer considered an intact layer for semi-rigid pavements. It's considered a significantly cracked layer, and the resilient modulus should be entered for simulating its stiffness value, but for an unbound aggregate base layer. The assumption is the crack spacing in that chemically stabilized layer are so close that the differential vertical deflections will be small relatively, and that there will be no additional movement at the cracks of the chemically stabilized layer itself. Thus, the assumption that it's going to behave as an unbound layer with a much higher resilient or elastic modulus. So coming back to the fracture mechanics model or approach for predicting reflection cracks, remember the shear component is defined by the low transfer efficiency, differential vertical deflection, which defines the shear component, and the fracture mechanics approach. The shear component, the increase in the stress intensity factors due to shear from incremental increase in number of load applications. But also remember that the increase in cracks is a function of combining the crack growth from the incremental increase in traffic versus the crack growth incremental in thermal cycles. And that also is related to the thickness of the material times the damage index, or the DI, the damage index, from the combination of the shear intensity factors. So the shear intensity factors are basically converted to a damage index basis for looking at predicting cracking over time by combining the two. So the stress intensity factor for each component is transformed into a damage index so that they can be added together, both from thermal as well as load. The damage index is basically defined by the increase in damage from an incremental increase in traffic and incremental increase in temperature cycles. And then the sum of that damage is used to predict the total damage at the crack tip. And then total damage is defined by the incremental increases in shear, bending, and thermal individually. So conceptually, that's how the thermal cracks are predicted, how reflection cracks are predicted throughout the life of the pavement by combining different types of modes and different types of shear stress intensity factors. So the cumulative damage index from the stress intensity factors is then used in the reflection cracking transfer function to predict the rate of reflection cracks, or reflection crack rate is then used to determine the length or area of reflected cracks that we can see and measure at the surface. Based on the length and or area of cracks predicted for the chemically stabilized layer. So the shrinkage, the fatigue cracks within the chemically stabilized layers are either entered or predicted by the software, and then our transfer function is used to predict the rate at which those reflection cracks propagate to the surface for what we can see and measure at the surface of the asphalt layer itself. So conceptually, this is the transfer function. And the transfer function has two coefficients, C4, C5, and DI is simply the damage index from the different shear and stress intensity factors from the different modes of loading and or crack propagation. So this simply shows now the term or coefficient in the damage term, the damage index, and or the transfer function. So the damage index stress intensity coefficient, that's the K1, K2, K3. K1 for bending, K2 for shear, K3 for thermal, and these are the coefficients for fatigue cracking and transverse cracking. So the damage values are basically independent of whether it's fatigue or transverse. They're basically the same, the K values. The C values, the damage index calibration coefficient, C1, C2, C3. C1 is the bending mode, C2 is the shear mode, C3 is the transverse mode. C1, these coefficients, C1 to C3, are different for fatigue and transverse cracking. So the bending mode are shown here, the shear mode, and then the temperature or transverse mode are shown in these two columns for fatigue and for transverse cracking. The calibration coefficients for the transfer function, C4 and C5, are shown in these rows. C4, they are different between fatigue and transverse cracking. C4 for the rate of reflection cracking, and C5 in the transverse cracking function for fatigue, and then the two values for transverse cracking. So the transverse cracks, reflection cracking for semi-rigid pavement reliability. Reliability was discussed in detail in Module 3 and how it is applied in the Pavement ME software. The standard deviation of the residuals for the semi-rigid pavements for transverse cracks is displayed on this slide. The standard deviation of residuals is used to determine the reliability as related to the transverse cracks of semi-rigid pavement. And so this is total transverse cracks, which include the reflected as well as new transverse cracks in the asphalt layer itself. And this defines the standard deviation of the residuals. And the graph below shows an example illustration. I believe it's at the 90% reliability level for thermal plus reflective transverse or shrinkage cracks. This now shows the total fatigue cracks for semi-rigid pavements reliability for fatigue cracks. And again, the standard deviation of the residuals for total fatigue cracking as a function of the total fatigue cracking predicted by the Pavement ME design software. The total fatigue cracking represents the reflective plus any new fatigue cracking, bottom-up fatigue cracking, and the asphalt layer itself. And so this is simply the standard deviation of the residuals for total fatigue cracking. Now let's move to finally the smoothness degradation for semi-rigid pavements. This is almost identical to what was covered on flexible pavement smoothness degradation, Measuring the smoothness is the same, using the same equipment. There is no difference for semi-rigid as opposed to flexible pavements. The basic design premise is basically the same between semi-rigid and flexible pavements. The same smoothness generalized model is used for semi-rigid pavements as applied to flexible pavements. So the semi-rigid smoothness degradation equation is shown here. Basically, it's the same type of model for flexible pavements. The IRI initial is the IRI after construction. The rut depth is the total rut depth measured at the surface or predicted at the surface. The average area of fatigue cracking, this is the total area of fatigue cracking reflected plus new fatigue cracks. And transverse cracks is the total transverse cracks, both reflective as well as new reflective cracks in the semi-rigid pavements. And then this is the site factor, and the site factor represents the same condition as was discussed for flexible pavements. And we'll mention it in the next slide as a reminder. The calibration coefficients, the C for total rut depth, 40.8, C2 for total fatigue cracking, 0.575, C3 for total transverse cracking, 0.0014, and C4, the site factor is 0.00825. So the site factor variable of the smoothness degradation coefficient for semi-rigid pavements is shown on this slide and is basically the same as for flexible pavements. So the age is simply the age in years. Precipitation, the average annual precipitation, the average freezing index, percent passing the 0.02 millimeter sieve. PI is the plasticity index of the material, subgrade soil, and the percent passing 0.075 millimeter sieve or the 200 millimeter sieve. That basically defines the site factor for a location for semi-rigid pavement design. So this just reiterates the calibration coefficients for the smoothness, semi-rigid pavement smoothness calibration, which were previously mentioned in the report or previously mentioned in the presentation. These values, as well as the other calibration values for semi-rigid pavements, are also included in the output for the Pavement ME software. And again, it's just a reminder, the values for the calibration coefficients for smoothness, reflection cracking, and the other values or other distresses of semi-rigid pavements may vary between different publications of the MEPDG Manual of Practice, depending on the results of the more recent global calibrations, the coefficients, and the exponents of the transfer functions for semi-rigid pavements are all included in the output report of the Pavement ME design software. And this is simply the standard deviation of residuals for the semi-rigid pavement smoothness, which is identical to the standard deviation of residuals for flexible pavements. So adjusting semi-rigid pavement designs. So we'll start with kind of doing a brief review like we did for flexible pavements on what should we be adjusting to when we get a design that doesn't pass the reliability level or the distress criteria for a specific design. So the asphalt layer adjustments mentioned specifically for flexible pavements discussed in the previous module 6-1 also apply to semi-rigid pavements. So these will not be repeated within this module. So this table simply, the table displayed on this slide simply illustrates the importance of the design factor or features related to the chemically stabilized layers in changing the distress variables. The two distress variables are total fatigue cracks, which would include chemically stabilized fatigue cracks, reflection cracks, and then IRI. And again, the definition of the number of checks that were discussed for flexible pavements also apply to semi-rigid pavements. So in summary, if we increase the thickness of the chemically stabilized layer, there's a significant effect on total fatigue cracks, whether they're reflection or of the chemically stabilized layer, and also reflection cracks. If we increase the flexural strength of the chemically stabilized layer, we have a significant effect on the total fatigue cracking from the chemically stabilized layer, but individually there is no impact on the reflection cracking other than from the reflection of cracks from the chemically stabilized layer. So there is an effect, but the effect is related to the total amount of fatigue cracks. So it's not specifically on reflection. A decrease in the chemically stabilized layer means there's also a significant decrease in total amount of fatigue cracks. The reason that there is an effect on reflection crack is that if the elastic modulus changes, in other words, it becomes weaker, then the crack tip or the stress intensity factors, as well as the load transfer efficiency, is probably going to change slightly across the cracks in the chemically stabilized mixture. The use of a crack relief layer, you can see, is not defined. The reason it's not defined here is because the Pavement ME design software was calibrated using crack relief layers on for a flexible pavement side, as well as a semi-rigid pavement side, as well as asphalt overlays of rigid pavements. So we will discuss this, its benefit and if there is a benefit, and the impact of using crack relief layers between chemically stabilized and asphalt layers in modules, specifically in modules 8 as well as 9, from a reflection cracking standpoint related to asphalt overlays. So the impact here will be reviewed in modules 8 and 9. The increase in strength of the subbase layer, which would be an unbound subbase layer, is a moderate effect regarding total fatigue cracks and a minor effect regarding reflection cracks. The increase in the thickness of the subbase would be a relatively low impact for fatigue cracks as well as reflection cracks. Treating the subgrade soil to improve the subgrade soil has an effect on the total amount of fatigue cracks and kind of a minor effect or minor impact on IRI and reflection cracks. On IRI predominantly from the site factor equation, and then requiring a lower IRI at construction, obviously has a significant impact on IRI, but has no impact on the other distress variables. Similar to reflection cracking and rigid pavements, there are other input variables that have a significant impact on the semi and flexible pavement distresses, but the designer does not directly control the inputs. That's like traffic volume, average annual daily truck traffic, climate or its location, and then the subgrade type. And so they basically all have some type of an effect on the total amount of cracking on the chemically stabilized layer. There is some effect, a higher effect from the traffic on reflection cracking, but also a minor effect on reflection cracks. And then climate and subgrade type do have an effect on IRI from the site factor. So now let's move to a summary of this module, what was covered in this module. On the summary, we're going to start with some points to remember that we discussed earlier in this module. The first is the chemically stabilized layer has flexural strength and can resist stresses. That's used in a semi-rigid pavement because that is the definition of a semi-rigid pavement. The chemically stabilized layer has flexural strength and can resist tensile stress. Another point is the suggested minimum layer thickness for the stabilized mixture is 6 inches. Another point is full bond is assumed between the asphalt and stabilized layer throughout the design period. So remember, if the user or designer wants to assume lower bond or no bond between the asphalt and the chemically stabilized layer, that is possible through the layer interface. But for calibration, full bond was used in all cases for new construction. And then there is a theoretical relationship between flexural strength and elastic modulus of the chemically stabilized mixture that defines the amount of cracking of the stabilized layer. And there is a unique relationship between strength and elastic modulus, all other variables remaining the same, at which the end of the design period you will end up with the same amount of fatigue cracking in the chemically stabilized layer. Continuing with the points to remember, the shrinkage or transverse crack spacing remains constant throughout the design period. An unbound granular layer is not permissible between the chemically stabilized mixture and asphalt layer. That basically violates the definition of a semi-rigid layer. The shear component of the stress intensity factor computations is by far the critical component for predicting reflection cracking. That relates back to load transfer efficiency and the differential vertical deflections across a crack. And now just reviewing a summary of the overall learning outcomes from Module 6.1. So there were 6 learning outcomes. The first, we defined semi-rigid pavements as it applies to the MEPDG. We identified the semi-rigid pavement distresses that are common and are the same for flexible pavements. We described the semi-rigid pavement transfer functions for fatigue cracking of chemically stabilized bases. We described the semi-rigid pavement transfer function for transverse and fatigue reflection cracking. We described the semi-rigid pavement regression equations for smoothness or IRI. And then finally, we identified the input variables that a user considered to change to achieve an acceptable semi-rigid pavement design. This ends Module 7 on the overview or on semi-rigid pavement design. This is an error on this slide. We're really ending Module 6 on the Semi 6-2 on rigid pavement design. And the next submodule of the training course sequencing will be Module 7 for an overview of pavement rehabilitation. To reiterate, this ends Module 6-2 on semi-rigid pavement design. The next submodule of the training course sequencing is on Module 7 for an overview of pavement rehabilitation.